stop here. This is the last slide that we covered. Right, so we continue on this. Okay, previously we have seen on one example where we did evaluate the closed loop transfer function, and when we changing the gain k, the closed loop pole is also varying according to the value of k, right, as in the table. And at one point, which is at k equal to 25, the poles location are located at the same place, which is -5 and -5. Okay, and then after -5, the closed loop pole will break away. One go to the upper side, the other one go to the downside, right? And if we remove all those closed loop poles that has been evaluated just now, so we can see what we can say finally it is called as the root locus. Okay. Okay. So now we're going to be to have another general concept of root locus rather than we doing some point by point analysis like that, which is somehow it is troublesome, where we need to try all those close gain, and then what are the closed loop poles. Okay, it is quite tedious to do like that. Okay, so now we using a more general concept where by having any transfer function, we still can sketch the root locus without doing the mathematical analysis like previous one. Okay, let's consider back the closed loop transfer functions that we have previously. Okay, so from these transfer functions, as what we always do, if we have a transfer function k s plus 1, s plus 2, s plus 3, normally what we did, in order to get the poles of this transfer function, we make the denominator here equal to 0. Okay, so in that case, we know that s is equal to 0, s plus 2 is equal to 0, and s plus 3 is equal to 0. So then that's, from here we can get s is equal to -2, s is equal to -3. So all these are the closed loop poles. Okay, so if we have a general transfer function like this, so we can also do like that. So in that case, we have 1 plus kgh is equal to 0. Okay, because this is the denominator of the closed loop transfer function. And then kgh is equal to -1. Okay, so kgh is equal to -1. So if -1 here, we plot it on the S-plane, where we have the real number and also the imaginary number. So -1 is actually located at here on the left side, -1. Okay, because it is a real number, not a complex number. So it is at the left side. Someone is not muting the. Let's check. Najmi. How can I mute? Okay, I mute. Right. Right. It is located at -1, real number. And if we consider, according to the vector here, so that being -1, And the magnitude from 0 -1 here is equal to 1. And the angles for this line is taken from origin, from here, quartile 1. Okay, and the angle is 180 degrees. Okay, so we can substitute here. The magnitude is equal to 1 and the angle is 180 degrees. Okay, so it is similar to what is written here. So the magnitude is equal to 1 and the angle is like this. It is written like that. So it makes more general, because 2k plus 1 is to represent that the angle could be calculated in positive side, or in reverse side, we also have negative 180 degrees. Or if we can have it full cycle and then repeat it again to this angle, so we're going to have 360 plus 180, which is 540. Okay, so the possible number should probably 540. And if we substitute k with 2, 4 plus 1 is 5, 580 is 44, and 900. Okay, so tak 58, 40, okay, 900. Okay, so this is possible angle. It could also be in negative side, 140 degrees, and negative 100 degrees. Okay, so in that case, we make it a general equation like this, where the k here is actually a value of 0, integer 1, integer 2, and so on. Okay, so we only consider it is equal to 0. So if 0 means that 2 times 0 plus 1 times 180, which is only 180 degrees value. Okay. So from here, we make a conclusion that the KGHS is comprised of one magnitude, and the other part here is the angle, right? So it is defined like this. So the magnitude is, if we back to here, so the magnitude is normally taken as the modulus value. Okay, so the magnitude is written as a modulus of KGHS, so it is equal to 1, and the angle is given, so the angle of KGH is equal to 2k plus 1 and 180 degrees. Okay, so this is what we call as the magnitude criteria and also the angle criteria. Okay. So thus a pole of closed loop system cause the angle of KGSHS to be the odd multiple of 180. If let's say, to make it simple, so the angle of a certain pole, if let's say I have a root locus, so the root locus, I'm using the same example as the previous that we have discussed. So the root locus is look like this. Okay, so if the we try with a certain pole that is lying, let's say it's located at here. So the pole is located at that pole. If we try on the magnitude and angle criteria, it would fulfill this both criteria. Okay, meaning that if we substitute KGHS when the S is equal to For example, here is -2, sorry, -5 and J3. Okay, -5 and J3. So we should every S here to this expression. Then finally we will got this value 1 equal to 1. Or if we evaluate the value of the angle criteria, so finally we will get this 180 degrees. Okay, later we will have a few examples to make it clear. All right, so from here as well, okay, from the magnitude criteria, we can rearrange. If you want the value of K here, so everything, the magnitude of G and HS here can be brought to the right, so it become like this. So K is equal to 1 divided by magnitude of G and magnitude of HS. Okay. Okay. So still using the previous example, so this value is actually taken from the table. So when K is equal to 5, we found that the closed loop poles are -9.47 and -0.53. Okay, so this is from the table, previous table in page 12. Okay, now we want to try to test whether this pole is really fulfilling the magnitude and angle criteria. Okay, so one thing that we can do is we try on the magnitude criteria. Okay. Okay, so if you use the magnitude criteria, so we have KGH should be equal to 1. So this is H. Okay, we have the K is just now 5 times, what is the GH? Okay, KGH. Okay, let's okay. So the overall transfer function is K divided by S plus 10. Okay. So if we substitute the S is equal to, for example, we're trying to use the first one, which is negative 9.47. Okay. Then we substitute all to S here. All right. And K we're going to use equal to 5. Right. So if you do that, so this going to be 5 divided by negative 9.47, negative 9.47 plus 10. And if you calculate it, you will get 5 divided by negative about 5 as well. It's 5 point something 0.19. Okay, which is it's about 1. Okay, so this is fulfilling the magnitude criteria. So this is the magnitude criteria. Okay, so it's fulfilled. All right, so you can also use the angle criteria to test whether it is fulfilling or not. Okay, but for the current situation, it is enough to use the magnitude criteria because every, for example, the gain K, the value of closed loop poles are available. All right. So you can also test it by using another point, which is 0.53, which is another closed loop pole, right? So negative 0.53 plus 10. And then finally, you will also, okay, so it's actually negative 1. Yeah, this is also negative 1. But the magnitude is we only taken the magnitude only without the sign. Okay, so if you're taking the magnitude, so it is actually 1 only. Okay, because our formula is with the modulus here, right? So that is the first one. Okay, we try on another example here. So we have this forward transfer function. So this is basically the kg, and the feedback transfer function is equal to 1. Okay, and then we want to evaluate whether this closed loop pole here is part of the root locus or not. Okay, so if it's part of the root locus, it should fulfill the magnitude criteria and the angle criteria that we found just now, right? So what we need to do first, so from here, we need to identify the open loop and, the zero and also the poles of the forward transfer function here, okay? It is not only the forward transfer function, it's basically the open loop transfer function, because the open loop transfer function from here is K, G, H, okay? So in this case, because the H here is equal to 1, so we still getting the same thing. Plus 1, plus 2. Okay, so we got the same thing because H here is equal to 1. So in terms of the 0, so we immediately can know that the 0 is negative 3 and negative 4, and the poles is equal to negative 1 and negative 2. Okay, then we locate this on the S-plane. So we have poles is equal to negative 1 and negative 2. So we place it here, 1 and negative 2. And we also have 0 and negative 3 and 4. Negative 3 and negative 4. So this is the first step. And then we locate the poles that we want to test, which is negative 2 plus J3, which is about here, negative 2 plus J3. Okay, so this is the testing poles that we want to know whether it is part of the closed loop poles or not, or it's part of the root. Okay, it's the same meaning. Okay, so next we need to connect between this testing point to all those zeros and poles. Okay, and then we note down the angle of each line here. Okay, we start on the 0 line. So we call it as theta 1 here. This is theta 2. The angle should be taken from the quartile 1, from here. Okay, Q1. Okay, so in this case, it is from here to here. So this is theta 1, theta 2. This is theta 3. So basically, theta 3 is a 90 degrees angle. And theta 4 is this one, theta 4. Okay. So as what we have done just now, we tried to use the magnitude criteria in order to test for the fulfillment of the the closed loop poles, right? So, but now if we try to use that, is it the same thing? So if we test by using the magnitude criteria, for example, we have KGH, suppose it's equal to 1, okay? And we have just now the S3412. Okay, S3, S4, S1, S2. Okay, and we put the modulus, and we want to test at -2 plus J3. Okay, by right, if we know all those parameters, we can solve for this, whether finally we get 1 or not. But the problem here is we don't know what is the value of K. Okay, the S, everything S can be substituted over here. But for now, we don't have the value of K. So in that case, we cannot use the magnitude criteria to check for the fulfillment. Okay, so we move on to another criteria, which is the angle criteria, where the angle criteria give us the angle of KGH is equal to 180 degrees. Okay, so basically it's plus minus 180 degrees. Okay. So the angle criteria, this is the criteria, but how we can calculate the angle here? So the angle of KGH is given by the summation of the angle of 0 minus the summation of the angle of the poles. So we have another formula. Okay, so it's basically come out from this statement. Angle criteria is given by angle of 0 minus the angle of poles equal to the odd of multiple of 180 degrees. So in this case, I'm just using 180 degrees. Okay. So let's say we consider back the thing that we have drawn just now. So we have the theta 1, theta 2, theta 3, theta 4, where this theta 1 and theta 2 is for 0, and this for pole. Okay, so if you're using this formula, so the angle of KGH is given by theta 1 plus theta 2, which is the angle of 0, minus theta 3 plus theta 4, which is the angle of pole. Or you can write it like this. If you open the bracket, then we have minus theta 3 minus theta 4. Okay? Then our task now is to get what are the values for all those theta that we have now. Theta 1, theta 2, 3, and 4. So we have to calculate the theta. Okay, for example here, for theta 1 here, we just need to use the trigonometry to get the angle of theta 1 here. Okay, for example, theta 1 is the tangent inverse of this, the opposite, okay, divided by the adjacent, right, which is 3 divided, so because this the height is 3, and the distance here is equal to 2, so divided by 2. Okay, so we got 56.31. 56.31. Theta 2, also the same thing, tangent inverse of 3 divided by this distance only 1. Okay, theta 3, we no need to calculate it because it is actually perpendicular. So it is 90 degrees. Okay, and theta 4, so you need to be careful here because theta 4 is at this part. Okay, so you can probably calculate it as theta 4 is equal to 180 minus tangent inverse of t divided by 1. 3 divided by 1. Okay, so you get the 100, it should be greater than 90 degrees. So now this value is correct, 108.43. Okay, so overall, we sum it together and we got this value, which is negative 70, and it is not equal to 180 as what should be in the from the angle criteria here, 180 degrees. It should be equal to 180. But for this case, it is not equal to 180. Meaning what? So that the poles that we are trying to test here is actually not part of the root locus of the system, not part of the closed loop poles of the system. Okay, because the root locus finally it will be look like this. Okay, the root locus going to be something like this, and another one is going to be like this, going like this. And if you look like to this root locus, this pole is actually far away from the root locus here. If let's say the pole is here, then probably it is part of the root locus. But now the testing point is far away from the root locus of the system. Okay, that's why it is not fulfilling the angle criteria that we have examined just now. Okay, let's evaluate with another testing point here, or the poles located at a new value, negative 2, and j sub 2 divided by 2 is basically 0.707. Okay, so if we compare with this one, probably the value is just at here. Okay, probably it is here. I'm saying like that. So this is probably 0.707. Okay, it's down from this original J3. Okay, so we trying we test with the same thing. Okay, just now we used the angle criteria, but now we are using the new value of testing pole here, which is negative 2 plus j and 0.707. Okay, so let's quickly writing here. KGH is equal to the summation of angle of 0, the summation of angle of poles. So still, by looking at this one, we're still considering all this angle, theta 1, theta 2, minus theta 3, plus theta 4. All right. So we need to evaluate again what is theta 1, but now because we already have the new height here. Okay, so we need to define tangent inverse 1 of 0.707 divided by 2, okay, and so on. Theta 2 tangent inverse 0.707 divided by 1, and theta 3 is equal to 90 degrees. Theta 4 is equal to 180 degrees minus tangent inverse of 0.707 divided by 1. Okay, so if you calculate carefully, these are the value that you will get: 19.47, 35.26, minus 90, minus 144.74, which is finally equal to negative 180 degree. So it is fulfilling the angle criteria. Okay, because this new location here of the pole is part of the root locus. So probably the locus should go like this, then like this. Okay. Okay, so it is part of the root locus close to pole. Okay, so once we get that it is fulfilling the angle criteria, we can proceed with another criteria, which is the magnitude criteria. And from the magnitude criteria, we have KGH is equal to 1. Okay, so we can calculate actually the value of K. That is what's supposedly the value of K at this point. What is the K at this point? So we can calculate 1 over GH. Okay, and previously we have GH is equal to 1 over K. It is, yeah, it's the one. S plus 4 divided by S plus 1, S plus 2. Okay, so this is still with the modulus here. I continue here. So K is equal to, so we bring up the third denominator here to become S plus 1, S plus 2 divided by S plus 3, S plus 4, and we still have a modulus here. And then we substitute with the point that we test just now, which is negative 2 plus J 0.707. Okay, so you have to plug into all these S using your calculator, but using the complex mode. Okay, using the complex mode, then substitute the S here to this transfer function. Then finally, you will get the value of K, which is equal to 0.33. Okay, so this is the first method. Okay, so this is the first method on how we can get the value of K. Okay, as you can see here, the formula is this one. K is equal to 1 over modulus of GH, which is also equal to this one. Second method, we can also using the second formula here, which is, this is not pi, this is actually the product. The product of poles length divided the product of zero length. Okay, so what you may see here, that I remove this one. Okay, so now we are trying to use another formula to get the value of K. Is this part. So this is the product. Okay, the product of pole lengths divided by the product of zero length. So where is the pole length? The pole length is the length from the testing pole here to the all those poles. Okay, the original pole from the transfer function, which is this point and this point. The zero length is the length between the testing point to the zero from the transfer function. Okay, so we can note down that accordingly, this is theta 1, so this length is L1, L2 is this one, L3 is this one, and L4 is this one. Okay, so if we define here, so we have the pole length is given by L3 and L4, it's the product, divided by L1 times L2. Okay, so here we also using the another trigonometry. We using the hypotenuse. Okay, if we have a hypotenuse like this, so let's say this is L1. So this is 2. This is, so this is not basically 3. This is another value. Yeah, this one. Okay, so this is 0.7. 707. So this is 0.707. Or you may remain it as the original values, square root 2 divided by 2. So this is the thing. So L3 is what? So L3 is here. So L3 is the distance between this point to this point, which is actually, we can take directly, which is equal to this value, because it is a perpendicular, okay, which is 0.07. I can write it here. Okay, it's 0.707 times. Okay, and then the next one is L4. So L4 is at this part. Okay, so L4 is basically, we have 0.07, and this is equal to 1. So L4 is 0.707 squared plus, yeah, plus 1 squared and square root. Okay, use the trigonometry properties. Okay, then we got the L4. So L4, you can write it, yeah, this is the value, 1.22. Okay, followed by L2, also similar to this L4 because it is symmetry, the position at the symmetry position. Okay, so L2 is also 1.22, and L1 we need to calculate it. So we have L1 here is 2, here is 0.707. Then we got the L1 by using the L1 0.707 squared plus 2 squared and square root. So we got 2.12. And finally, we have the same answer as what we did from the another formula here. Okay, we use this another formula. We also got 0.33 for the value of K. Okay, so it's open. You can use either way. You can use the first formula, or you can use the second formula. That is the trick here. So another example, also the same thing. We want to test whether this pole is part of the root locus or not. Okay, basically negative 3 plus J0 is negative 3, right? Because we don't have any value of the imaginary. Okay, so we get the 0 is negative 2, and the poles are, so we have to take the roots here. you have to find what are the roots for that one. So it's going to be -2 plus j3 and -2 minus j3. Okay, so with the same procedure, we locate the 0 and also the poles. So the 0 at the -2 here, and the poles are -2 plus j3. So here, so this is j3, and we have another one here, -j3. So this one. Okay, so we have located all those pole and 0 from the transfer function. Now, the test point is at -3. So we have another point here. This is not, currently it's not the pole. It is just a testing point, -3. So we connect all this to the poles and 0. Okay. So we start on the noting down the angle. Start for the 0 first. So this is theta 1. This is theta 2. And this is theta 3. Okay. So if we use the angle criteria, so AGH is equal to 180 degrees. We haven't decided yet. So we remove this one. Oh, why my eraser is not working here? K is equal to GH. So it is equal to summation of Z and summation of pulse angle. Okay. So we have theta 1 minus theta 2 plus theta 3. Okay. So now we calculate theta 1 is 180 degrees because it just aligned at here. So the angle is calculated from here to this point. So it is 180 degrees. Okay, minus theta 2 and theta 3. Okay, so you can calculate as usual. You can probably use this triangular here to calculate the value of angle over here. Okay, then probably 270 minus this angle. So you got this remaining angle here, right? This is one. And for this one, probably you use a similar one, 180 degrees minus this angle. So you, sorry, not this angle. So it's not 180 degrees, probably 90 degrees plus this angle. So you got the full of theta 3. Okay. But actually, you no need to do like that because as you can see here, the testing point here make the symmetrical line between the upper part and the bottom part here. Okay, so in that case, actually this angle is conjugate with this angle. Okay, so meaning that this angle theta 2 here, if you plus with the angle theta 3 here, it will make a full 360 degrees. Okay, so basically here, a theta 2 plus theta 3 is actually 360 degrees. So finally, we have 180 degrees. Then this is fulfilling the angle criteria. It's plus minus 180 degrees. Okay, so that's how we solve that one. So similar with this one, I will not solve for the whole. You can try by yourself, but I try to initiate what are the location of the poles and zero. Okay, so if you extract from this one, the poles, the zero are -2, and you have to take the roots from here, and you will get -1 plus J4 and -1 minus J4. Okay, and for the poles here, we have -10, and from this one, we have plus minus J3, or plus J3 and minus J3. Okay, so locating all those pole and zero, so we do have -2, sorry, this is 0, not pole, 0, -1 plus J4, so for example, it is here, so this J4, and this is -J4, so we have 1 to 3 pole, 0, and we also have 3 poles. So the poles are -10, which is a bit far away here, -10, plus J3, so it is just imaginary number, so it is here, J3, it is here, J3 negative. Okay, so we have done all. Then we locate the value of the testing point that we want, which is at the -9. Okay, and then we connect to all the poles and zeros. So we have this one, we have this line, we have this line, we have also this line, we have this line, and finally we have this line. Okay, next we define the angle. So let's say I start with this one. I start with the 0, θ1. So this is θ2. This is θ3. θ4 is for start from for the poles. Okay, let's say the poles number 1 here. Okay, what is actually the angle here? θ4. Okay. 2, 3. One, two, three, 4, 5. Okay. Let's say I take this one first. θ4 is this one. Is this one. And θ5 is this angle from here to here. And we actually have θ6 for this pole. But θ6 here is actually 0. Okay, because the line is at here, and we point at this pole, and this line angle is 0 angle. Okay, we are not looking at from here. We look from the pole. For example, we look from this pole, and what is the angle to this point? And for this, we also look from the poles, and the line is here, so the angle is equal to 0. So if we use the angle criteria, so KGH is equal to θ1, this one, plus θ2 plus θ3, is all for the zeros, minus θ4 and θ5. If you like, you may also include θ6, but θ6 is 0. Okay, so you can find out what are all those angles. So basically, we can make it simplify it. This is actually 180 degrees. We can solve it very quick actually. And again, if you look at this connection, there are also symmetry between upper part and bottom part. Okay, so for example, just now, theta 2 here and theta 3 here is conjugate each other, the location. Okay, so theta 2 plus theta 3 is actually 180 degrees. Minus theta 4 and theta 5. So theta 4 is here and theta 5 is here. Also, it is conjugate and it also gives an 180 degree. So if we sum it all, so we finally got it is equal to 180 degrees, which is fulfilling the angle criteria. And after that, you can calculate the value of K. Depend on you whether you want to use the first formula or the second formula. Okay, so if you use the first formula, you just need to reverse this transfer function because K is equal to 1 over GH. Okay, so if you substitute GH over here, the denominator of GH here will become the numerator here. Okay, so in that case, actually it is equal to, just need to swap the location. S plus 10, S squared plus 9 divided by plus 2, S squared plus 2S plus 17. And with the condition of S is equal to negative 9. So you need to substitute negative 9 here to all those S over here. Okay, then finally you will get what is the value of K. And it's suggested that the value of K is equal to 0.161. Okay. I think that's it for today. Okay, is there any questions so far? Are you still with me? Any questions?
No, doctor.
Okay, thank you.
Doctor,
Hmm?
can I scan the attendance?
Yes. Okay. Oh, already expired. Probably. It is just probably expired. Okay. For the others, we may dismiss right now. Okay. While I'm trying to regenerate again this QR attendance. Thank you very much, all. See you again next week. Okay. Thank you.
Doctor.
Welcome.